Hi, in this video, I'll introduce how to solve a linear differential equation of second order that's non-homogeneous with constant coefficients. I'll be deriving the general approach in this video, and in the next two videos, I'll talk about the method of undetermined coefficients and the method of variation of parameters. All right, so here's the form of the equation. Ay double prime plus by prime plus cy equals f of t. This is a non-homogeneous linear differential equation of second order with constant coefficients. First of all, when saying linear, we mean to say that the y and its derivatives are not raised to any power. They're not inside of any other function. They're not multiplied by each other. They are linear in the linear combination sense. Second order means the highest derivative is y double prime. Constant coefficients means when we did the linear combination of the y and all its derivatives, the coefficients that go with it are not functions of x, they're just numbers. And the important word is actually the first word is non-homogeneous, and that refers to the fact that when you move all the y's to one side and everything else to the other side, then you get a non-zero function of t on the right side. Okay, if it's zero is homogeneous, it's non-zero is non-homogeneous. All right, so suppose we already found a particular solution y sub p that solved this equation. So that means if we plug in the equation, it should be true. That means a yp double prime plus b yp prime plus c yp is equal to f of t. So guess what else is also a solution? If you're only looking at the left side of the equation and imagine that it is part of a homogeneous equation, meaning equal to 0, then we know how to solve it for y1, y2 that are linearly independent, right? So if those are linearly independent solutions of the homogeneous version, then plugging it in, we should have it all equal to 0. Ay1 double prime plus by1 prime plus cy1 should be 0, and the same thing with y2. If we multiply the y1 equation by some constant c1, then the right-hand side is still going to be 0, and the same thing with the y2 equation. The right-hand side is still going to be 0. So now we have three equations. We're going to add them side by side and check out what happens. All of these terms that have a common factor of a, right? I can factor out the a. And check this out, because derivatives are distributive over a sum and multiplication by constant, and that means that whole thing in parentheses is just being taken to the second derivative. And then I can do the same thing for b. And I can do the same thing for c. And on the right hand side, I have f of t plus 0, which is just f of t. So in other words, that grouping that's in parentheses, that is also a solution to the equation. In fact, that's it. That is the solution. That's what the existence and uniqueness theorem says. It says, given the initial value problem, where the equation is ay double prime plus by prime plus cy equals some function of t, and initial conditions on y at some time t0, and y prime at the same time t0, and suppose there's a y sub p that is a solution to the non-homogeneous version of the equation, we call it the particular solution. The particular solution is a solution that plugs in and gets us the non-homogeneous version. And suppose that we have y1 and y2 as the linearly independent solutions to the homogeneous equation. And we already know from solving homogeneous equation that a linear combination of y1, y2 is the general solution to the homogeneous version. And suppose there are solutions in some interval I that contains the point t0. Then there exists one and only one solution to the initial value problem, and that solution is y sub p plus c1y1 plus c2y2 for some constant c1, c2, and we get them out of the initial conditions. The equation gives us the yp and y1, y2, yp for the non-homogeneous version, y1, y2 for the homogeneous version. The initial conditions help us determine what the C1, C2 are. So that's the existence and uniqueness theorem. It's important, so I'm going to box it up. Using the same method of adding things side by side, we can prove the superposition principle. Now suppose the f of t that's on the right hand side is the sum of two functions f1 and f2. Then it may be too hard to try to find a yp that fits both of them at the same time. And suppose that maybe it's easier to find two separate solutions, u1 that goes with the f1 and u2 that goes with the f2. u1 is a particular solution for f1, so it fits the equation with f1 on the right hand side, and u2 fits the equation with f2 on the right hand side. Then guess what happens if we add side by side? The a terms, we can factor out the a, and you have u1 double prime plus u2 double prime. And again, because the distributive property will take the double prime on the outside. And the same thing with the b terms and the c terms. And on the right hand side, we have f1 plus f2. So what that means is that the u1 plus u2 is a particular solution to the non-homogeneous equation. So that's what the superposition principle says. If u1 is a solution of the non-homogeneous equation with f1t on the right-hand side, if u2 is solution with f2t on the right-hand side, their sum is the solution of the equation for the sum of f1 plus f2 on the right-hand side. This principle is also important, so I will also box it up. So if I put the existence and uniqueness theorem together with the superposition principle, then I can find a way to solve a general non-homogeneous equation. Given the equation, the steps to solve it are these. Number one, solve the homogeneous version for y1, y2, linearly independent. Step number two, you find one particular solution y sub p to the non-homogeneous version. Part of that step two, and let me call it step 2a, is the superposition idea. If the right-hand side is a sum of many terms, and it's too hard to try to find a yp for that matches the whole sum all at once, then find separate particular solution for each term and then add them together to get y sub p. Step 3 is to write the general solution as y equals y sub p plus c1y1 plus c2y2. Okay, in other words, a particular solution plus a linear combination of the homogeneous solutions. And finally, step 4, if initial values are given, then you plug in the initial values to solve for C1 and C2. There we go. Box it up. All right, now, how do you go around finding the particular solutions? So in the next two videos, I'll explain two methods, the method of undetermined coefficients and the method of variation of parameters. All right, that's general idea. Hope that helps. Thanks for watching. Bye.